Hello everyone. So today we're going to be doing Lab 7. So this is going to be making a state machine with ROM and with equations. So in this lab, you guys are going to be implementing the state machine from your homework assignment, which is this one right here. You need to do it two different ways to support both ways, one with the ROM, one with the equations. This is going to be a very involved lab compared to the previous ones. So I definitely made sure to do a very good job in this video. Like this video, I spent a lot of time preparing for it. These are some very foundational principles that need to be taught properly. Okay, so this right here, pretty much what we're going to be doing this video is this state machine. We're going to go through the process step by step from scratch, how to make this entire state machine in Verilog using both a ROM and with equations. So to start off, let's discuss how it would work with a ROM. So the very first step is to pretty much just make a truth table or a state table describing the entire behavior of this. So let's say we're here in state S0. So we're going to encode that with 0, 0 for Q. It's like 0, 0, decimal to binary. You always want to encode your states in binary because yeah, that's just how it is. So state 0 get 0, 0. State 1 get 0, 1. State 2 gets 1, 0. And state 3 gets 1, 1. So, and these are inputs. These diamonds, these are the inputs. So x0 is an input, x2 is an input, x1 is an input. The things in the rectangle, those are states. Um, these right here, these bubbles, those are outputs. And what else is there? Oh yeah, and this one right here, this is different, and this is a more state, and these are melees, where the melees, it's associated with the link. So the output in a more, right here in state 3, the output is associated with the state, which is why it's written in there. But for state 0 and state 1, the outputs happen when you transition to another state. And that's one of the ways that the melee machine is more powerful than the more, in that it can sort of behave kind of both sequential and combinational together, because it's the state, the output happens independent of the state, but for the more, it happens in the state. Okay, well, so we might be thinking, well, how do we make the state transition diagram? Well, from this chart, this diagram, we can just brute force it. So let's say we're in state 0, and input x0, x1, and x2 are all 0. What's going to happen is we're going to go to state 1. So that correlates to this first row right here. We're in state 0, which is why Q1 and Q0 are 0, 0. Like right here, Q1 and Q0 are 0, 0. And then the inputs, when all of them are 0, the only one that matters here is this one. It goes there. So then it goes to state 1 and outputs nothing. So it goes to state 1, outputs nothing. And then, and then for this one right here, well, you might notice that the only thing that matters is x0. So even though when we're in state 0, there's 8 possible things for that could happen in state 0 depending on these inputs, the only one that matters is the stuff that happens for here. So when this one is 0, it does this. When it's 1, so um, so when x0 is 1, x1 is equal to 0, x2 is equal to 0. It goes this way. And it just doesn't even matter what these two are. It can be anything. It's just when x0 is 1, it goes here. So then z1 is a 1. So z1 is a 1. The other outputs is 0 because there's no bubbles for those other outputs. And it goes to state 2. This is state 2, 1, 0, 1, 0. And these other ones, they're all going to be identical to these first ones. Like you just can duplicate it, and go down. Only when you get to, let's do this one right here. 0, 1, 0, 0, 0. So when we're in state 1, all the inputs is 0. Well, that means if all of them are 0, then x2 is going to be 0. So then we're going to go there. So that means it would go around back to S1. So 0, 1, the next state. And then the only thing that gets turned on, the only output is Z2. So 1, 0, 0. So that would be this row. So in your lab, you're going to have to pretty much go through this whole process, but for your own state machine. Let's reconnect. Okay. So this right here is the cohesive state table for the entire thing. Let's go in front of it. I'm gonna get this. Oh, I know. Okay, now it's all fitting in the screen. Okay. So when we're in state 0, these first 8 inputs correlate to that. When we're in state 1, these second 8 correlate to that. When we're in state 2, this third set of 8 correlate to that. And when we're in state 3, this last set correlates to that. So let's just recap real quick. So when we're in state 0, 0, it means we're here, and x2, x1, and x0 are all 0. We go here to state 1, which is why q1 plus, q0 plus is 0, 1. As it goes from state 0 to state 1, which is 0, 1, that's the next state. And yeah, when it's a plus, that means it's the next state. And when we're still in state 0, but when x0 is 1, we go to state 2, which is why it's 1, 0, the binary value for 2. So we go there and output z1. So z1 gets an output. Okay, and all of these rows that come after, they're pretty much clones of the first two, because the only determining factor of what happens is x0, and x0 is 0 here, and it's also 0 here, so that means this row is going to be the same as this row. And same thing here, this x0, 0 there, so this one's going to be the same as this one and this one. And then for state 1, let's say we're in state 1, and all the inputs are 0, including x2. Then we're going to output z2. So we put a 1 there. And then we're going to go back to state 1, which is why these two are 0, 1. And then, yeah, when x2 is 1. So, oh yeah, and then these first 4 are going to be the same because x2 is going to be 0 for all of these first 4. And that's the only thing that matters for state 1. And then when x2 is 1, which is what's shown in these next 4, you can see that the next state is state 3. So we're in state 1, which is why it's 0, 1 here. And then we get the inputs where x2 is 1, and then x1 and x0 don't matter. So these two don't matter, these two don't matter, these two don't matter, these two don't matter. It's only that first one that matters, because that's right here, x2. What's going to happen? Fucking right on that. Weird. Okay. But yeah. So yeah, that describes that first row. Let's go through this one. So we're in state 2, right here. When x1 is 0, it goes to state 0, so x1, 0. It goes to state 0, so it's 0, 0. And there's no outputs. There's no output there, and there's no outputs in the links. So it's 0, 0, 0. When x1 is 1, it's going to be, so that middle one, this one right here. When x1 is 1, the next state is state 1, so 0, 1. There's 0, 1 there. And again, there's no outputs. 0, 0, 0. And yeah, so that's how you know how to fill out the state table, by looking at this directly. So once you have that, let's go into Verilog here. Okay. So once you have it all filled out, we're going to need to make a ROM. Well, in your lab, your job is literally only to fill out these values, but which you should hopefully know how to do now that we went over some examples. And you'll be able to access everything that's video in Blackboard. So this example should help. It should really help. So this is pretty much the same thing as your lab, but with just a different state machine. Okay. But if we were to make this program from scratch, we would need to make our own ROM module. So we would make 4 bits, 5 bits there, and 31 there. So that would correlate to like, so it's 5 bits long for the number of columns. So that's what this is. And 32 all the way down for the number of entries. Because in this truth table, there's going to be 32 entries. 8 for the first state, 8 for the second, 8 for the third, and 8 for the fourth. So for a total of 32. And yeah, and then the way you would assign the first one is ROM 0 is equal to 5 tick B 0 1 0 0 0. And this 5 tick B, that's just the notation of how you declare a number in Verilog. So the number up front, that's how many bits you want to represent it. The tick is just something you always put for syntax. And the number indicates the radix of these digits. So if you put B, then you have to write it in binary. If you put D, you can write it in decimal, like 17 or 28 or 24. Or if you put hex, you can write it in hexadecimal. Okay. So when it's all done, you should get something like this. We're going to have a ROM, which is pretty much just this table. And a ROM is a combinational device, meaning that whenever inputs are applied here, the output instantly changes. But these flip-flops, alright, let's try and release this to the table. So yeah, you see how the inputs of the table correlate to the inputs on the ROM, and the outputs of the table are the outputs of the ROM. So yeah, that's how that works. And this is our clock. Flip-flops. Let's reconnect. Okay, so now that we know what our entire structure is going to look like, we're going to have a ROM, and our flip-flops. We're going to need to, in Verilog, make a module for the ROM and a module for the flip-flops, and then instantiate them together to form this entire structure. And yeah, let me think about this real quick. And if you're new and you don't, let me just try to explain what's going to happen from a high level perspective. So this is a state machine, meaning that in every tick of this clock, these flip-flops right here, they're going to take whatever output is on this line and from this line, and then transfer it over to this line and this line. So for state 0, 0, and then these inputs are 0, due to the combinational logic that's in here, it's going to instantly change this and these outputs to be what should happen for the next state. And then the clock is going to tick and then bring these values here to here, updating this, which will then change this. And that's going to go on again and again to emulate the behavior of this entire thing. So, yeah, I'm sure most of you guys already knew that, because that's what a state machine does. But just in case anyone didn't know, just wanted to say that. Okay, since our top module, cover that later. Okay. So the D flip-flop, that's going to be so this right here and this, these are our D flip-flops. And the way we make one is with this module. So as you can see, there's one input, one output, and then the clock. So that's why those go into sensitivity list. We've got our input D, we've got an input for the clock right there, input for the clock, and output Q. So that goes there. In a normal flip-flop, there's the Q not output, but we do not need that in our state machine, so we can just forget that. So we're going to initialize the outside of Q to be 0, just because, so it's not floating or anything at the start. And then always on each positive edge of the clock, it's going to shift this value here to here. So yeah, what that means is let's say D is 1 and the Q is 0. So this is D. Let's do a little timing diagram. D, Q, clock. So Q is 0 this whole time. D is 1. And then the positive edge of the clock, Q is going to be updated to D. So it'll become 1, and then this will just stay 1. So like for that example right there, it's the clock. So that's how flip-flops work. It can only change when the clock changes. So on this rising edge, and that's what this Verilog code does. It says always on the positive edge of the clock, assign output Q to whatever the input D is. So that's how you make a flip-flop. So the next big thing to do is to make ROM. So ROM, we have Q1 and Q0 and the X's. Those are our inputs. And these X's, those are the physical values on the switch. Like on right here. These switches, those are the inputs that correspond to X2, X1, and X0. So the switch right here is going to be X0. This one is X1. And yeah, you get the point. So you physically have control over what these are by switching the switches. So all these are our inputs and these are our outputs. So that's what goes in our sensitivity list, since that's the sensitivity list is always where your inputs and outputs go. So we put our inputs and our outputs. Z2, Z1, and Z0 are going to be represented by the LED outputs on our board. And then Q1P and Q0P. Those are the outputs of the ROM. So yeah, you guys get the point. We want to make a ROM, so in the sense, and we have our inputs and we have our outputs, and we have to put all of that in the sensitivity list because you always put your inputs and outputs there. Inputs these, it's those. So we wanted to make a 5-bit ROM that has 32 entries. That's how you do that. And then we want to initialize it with all the values we had in our state table. So this table right here, this is what you think about manually. And once you have that thought out, you go in here and you initialize it all. So yeah, that's what this was. And then once you have that, you need to make an index. Remember, the ROM has all these values, and we need to make it be when 0, 0, 0, 0, 0, 0, 5 zeros are entered in. It outputs this. So our index is going to be Q1, Q0, X2, X1, and X0 in that order. So that's why we do that here. And then we want to assign our outputs. So Q1 plus, we're going to assign that Q1 plus, that's this guy right here. Q1 plus, that's going to be equal to ROM index. Index is going to tell it which row it is. So if index is 0, corresponds there. But since we're assigning the value of Q1P, we need to know what index it is here, like this one. That one's the 4th. So it's 4, 3, 2, 1, 0. So the column that corresponds, so yeah, this is the column. So yeah, QP, it's going to be equal to whatever index. The index is going to be the 5-bit value telling us the row. And that's going to be dependent on these things, which is why I use index for that. Because if X2 and X1 change, index will change, which will then update the location that we need to look at. And Z2, and here for Q0 and P, it's in the 3rd row, so that's why, 3rd column, so it gets a 3. Z2, 2nd one, gets a 2 there. Z1, the 1st one, get a 1 there. Oh. So you always have to exit out of the app with this one. Okay. So yeah, you guys know how this works. So yeah, this is the ROM now. So now that we have those modules built, we need to instantiate them. So we instantiate them here. And then we define our internal signals. Or actually, let's define our inputs and outputs. So What we want to do is we want to have a button that controls the clock, and then we're going to have the FPGA clock. And I'll get into this later why we need two things for the clock. And then we have our input X, which is going to be mapped in the constraint file to the switches. Output Z, which is going to be mapped to the constraint file LEDs. Then we have our state, which will be mapped to LEDs too. And then we have our cathodes and anodes, which will be used to display a number. And then we have our blink, which is going to be used to show when the positive and negative edge of the clock occur. Okay. Let me check, move this over. So this right here, Q1P, like, so Q1 plus and Q1P are the same thing. You can't write a plus sign in Verilog, so I used P. And I made these two wires because they're internal signals, which is why they're in between two modules. Do you see how it's in between the ROM module and this one? The ROM and D flip-flop. And then those two wires of Q correlate to these two. And then I assigned state to be equal to Q, where it's like we're going to have our LEDs. So we got LED. These are two physical things on the board that we want to show the state that we're in our machine. Rather than just assigning it directly, I had to create the actual wire coming out like this, I think. So that's what that does. Because we know these two are Q. So if we assign state to be equal to Q, that's like making a whole nother wire going out. Yeah, so that's that. Maybe it would have been just simpler to just have Q be an output. But I don't know, I just decided to do that way. Okay, so this right here. So every time we have our slow clock on the positive edge, a red LED on the board is going to blink. So here it's going to blink, here it's going to be off, here it's going to blink, and it's going to do that slowly, because that's the slow clock. And then here's where we instantiate them all. So yeah. Trying to explain this real quick. So in our ROM module, we've got our Q1 and Q0. So that's these, which also, so yeah, Q1 and Q0, which are also connected to the output of the D flip-flop one. So that's why this is here, but it's also here in this flip-flop. And then for the other flip-flop, it's there. Like you see how in the D flip-flop, the third entry is the output. And then in the ROM, these two are the inputs. So yeah, that corresponds to this one, and this one. So yeah, I hope you guys make that connection. Okay. Oh, and then this is another one that's connected to. So the output of the ROM, the Q1P and Q0P, is going to go into the input of the two flip-flops. So this is the output of the ROM, which also goes into the inputs. And then, oh yeah, for the clock. So this is what I was referring to earlier. We could just have the clock slow, just go and connect it directly, but that wouldn't be good because we want to have control of when it goes to the next state. So what we're actually doing, making an AND gate, we have our clock, and then we have a button. So when the clock's ticking like this, if the button's 0, this is going to be 0, and if it's 0, then the clock input, it's just going to be a flat line. So you're never going to get that positive edge. That won't happen. But when you set the button, when you press the button, so you press it down, a 1 gets sent here. So what that means is that this side and this side become the same. So all of a sudden, the clock starts working, and it happens when you press the button. But when you let go of the button, it all just stops. So yeah, that makes sense. So yeah, this is 1. If this is your waveform on the clock, this will be your waveform on the output. But when this is 0, the output of the AND gate will always be 0. So yeah. Oh, and that's what this is right here. This right here is a primitive. This is a primitive in Verilog. So primitive is the simplest like building block that you can use to make a gate. And the first thing of the port list of a primitive is always going to be your output, which is going to be, I named it wire BTN underscore CLC, so for button clock. So this right here, that's like the wire BT and CLC underscore. This wire goes in there and then goes into there. And then the inputs, obviously, it's gonna be the slow clock right there. And then the physical button we press. So once you do all of that, you'll it should be working. Oh, and then yeah, this right here. So this is a module that it takes in the state, which is going to be a 2-bit value, and depending on that value, is going to set up the cathodes and anodes to display the number that it is on the 7-segment display board. So right here, it's going to display the number. So yeah, let's program the device now. Reconnect. So let's program the device. Try and stabilize it. You really can't see it too good. Let's see if we have a flashlight will make it clearer. Hold on. Man, this is annoying. Okay, whatever. In the 7 segment display, it's a 0. I'm just trying to let's move that and do something. Covering this. Make it worse. A lot worse. Okay, whatever. So, hold on. So let's test this out. So this is going to be very similar to the demonstration you need to show in the lab. So when we're in state 0, 0, right now everything's 0. So there's going to be no output. But if we change X0, which is this first switch, to 1, then according to that, Z1 should turn on. And Z1 is this LED right here, because this is Z0, this is Z1, and this is Z2. In your lab, Morton used different indexing, so he did Z1, Z2, Z3, but I used Z0, Z1, Z2. So when we turn X0 up, so this one, when we set the switch from 0 to 1, this LED should turn on. So let's do that. And it does. So what that shows is that this right here, full area, is functional. Like, this is all good. So it's set to 1, but now when we press the button, it's going to go to the next state. It's going to go to S2. So this number in the 7 segment display is going to change from 0 to 2. And it does. It changes to 2. You can barely see it, I think. And it doesn't matter what the inputs are in the state, there's going to be nothing. Because there's nothing here, and then there's nothing in the links connecting it to anything, so there'll be never ever be an output for state 2. And let's say we want to go state 0. Well, then what we'd have to do is set x1 to 0, which is right here. Or if we want to go to state 1, we have to set x1 to high. So let's go to state 1. So this middle switch right here goes high. And then I press the button. Okay. So I press the button, and it changed to 1 now. And then Z2 turned on because X2, this third switch, is 0. So it's like doing this in a loop now. Well, yeah. But if you were to change X2 to 1, this would turn off. And then this would turn on. So if we do that, So yeah, Z1 turns on. Z1 turns on. And then if we press the button again, it'll go from 1 to 3. So yeah, it changed to 3. So from here to here. And then when you're in state 3, this is the more part of the state machine. So outputs Z0. So you can see Z0 is on. It doesn't matter what the inputs are because the output is dependent on the state, not the inputs. And then when we press the button, it's going to go back to state 0 no matter what. And it changes to 0. The number right here changed to 0. So that's how you do it with a ROM. All of the code will be available in a folder on Blackboard. But yeah, this is just the first way of doing it. The second way of doing it's going to be with the equations, which fortunately is much, much easier. Okay, so to do it with the equations, all we have to do is get an equation for each state and then each output. So the very first step is to encode all of your states. State 0 gets 0, 0. State 1 gets 0, 1. State 2 gets 1, 0. And state 3 gets 1, 1. And once you've done that, to get the equation for state 0, for bit 0 of your flip-flops, what you do is you look at these four and you find all the ones where Q0 is 1. So for state 0, 0, that does not apply. For state 2, does not apply. But for state 1 and 3, you can see Q0 is 1. So those are the two we're going to be analyzing. So what you want to do now is, now that you know which one has a 1, now that you know which one has Q0 as a 1, you need to find all of the places where something comes into that state. So there's an arrow here, an arrow here, and an arrow here. And then in this one, there's an arrow there. So for this one, so let's do 1, arrow 1. Where does it come from? It goes here and all it comes back from here. So it comes from when Q1 is 0, so it's going to be Q1 prime, because if it was 1, it would just be Q1, but it's 0, so it's Q1 prime. And then Q0 is 1, so it's just Q0. So that's there. And then X2 has to be 0 too. So this first one happens when you're in state 1 and X2 is 0. The second one comes from here, so it's 0, 0, so Q1 prime, Q0 prime, and X0 prime. Third one, it's been Q1, Q0 prime, X1, because you're here in this state. And yeah. And same thing for Q1. Let's go through these real quick. So for state 0, this one's easy because the only place in the entire diagram where state 0 is, output 0, Z0 is high, is in state 3, so it's just 1, 1. Hold on, accidentally. Okay, good, it's there. What was I doing? Oh yeah. Okay. So for Z0, it only happens in state 3, which is 1, 1, Q1, Q0. So it's just Q1, Q0. Z1 only happens when it comes from here and it comes from here. So there's going to be two different lengths. First one is when it comes from state 0. So that's this one right here. Q1, Q0, both primed because it's state 0. And then X0, it's just X0 because it's a 1. And then there you go, you get that one. And then the other one is from state 1 going into X2. So in state 1, Q1 is low, which is why it's Q1 prime. Q0 is a 1, so it was there. And then X2 is a 1, so it was there. So is that Z2? Only time Z2 happens is when you're in state 1 and X2 is low. So Q1 prime, 0, and then Q is 1, and then X2 is 0. So yeah, that's for Z2. Yeah. So now let's open up our Verilog code. Oh yeah, and this right here, this is the diagram of what's going to happen. So it's a lot like the ROM, where we're going to have this, except instead of it being a ROM that just sets fixed output of tables, this is a combinational network where there's gates. So for Z2, it's an actually we'll do Z0. Z0 is the logical AND of Q0 and Q1. So that gives us Z0. For Z1, it would have been two AND gates going into an OR gate, and then a bunch of stuff. And then there'd be inverters and everything. But yeah, it's just a huge combinational network going on in here, which is represented by these Boolean equations that we made. Okay. So yeah, let's open it up in Verilog. Okay, yeah, so these are the equations that we just derived. And all we need to do is instantiate the D flip-flops. And then have our clock be button clock because we want it to be when we press the button with the AND gate. And then the input is so the assign statements make these 5 outputs. And this output Q0, Q1 plus goes into the input of 1D flip-flop. So that's why that's there. This output that we assigned goes into the input. And then the output of that flip-flop, this output goes back into the combinational network, which is why it's reused as an input to calculate the next set of outputs. And yeah, same thing for this flip-flop. It takes the physical output from here. From this sign, we just instantiate the D flip-flop and use that output as an input. And then the output is here. It goes around from here, back into there. Gets reused as an input in these equations. So yeah. And then if you generate the bit stream, you'll get an identical behavior to what we saw in with the ROM. So yeah, this entire video was just showing you how to do it all from scratch, the entire thing. Your guys' job is to just get the equations, and then from this thing, and you can simplify it if you want, but if you don't simplify it, it won't matter because Verilog will just make it work anyway. Yeah, I guess I'll just go over how he got Z1 in case someone is confused. So for Z1, we're going to have to find all the places where Z1 is. That comes from here, here, and here. Is there anywhere else? Nowhere else. So remember state 0, 0, 0. And x2 is 1. So it's going to be, and just like q1. So the first term is going to be q1 prime. It's prime because it's 0. And q0 prime x2 plus and then the next one is right here. And because that's in the states, it's in the box. All you just do is write whatever the state is. So it's state 1, so it's 0, 1. That means q1 is 0, q0 is 1, so that means it's going to be q1 prime q0. And then this last one right here, it's going to be plus state 2, so it's 1, 0. It's going to be q1 q0 prime. So let's see if that's the same thing he got. So q1 q0 prime x2 plus q1 prime q0 plus q1 q0 prime, yeah. So this right here just shows the methodology of how you can properly get these, and it's the same thing for the inputs, except the q0 and q1. What you have to do is use what I said earlier, where, let me erase this all. So we'll do Q0 because he already gave it. I can just do it all. So for Q0, what we're going to do, we got to label all the states, obviously. So that was 0, 0. This one 0, 1, and this one's 1, 0. So remember the first one is Q1, second one is Q0. So for Q0, we need to find all of the states where that's 1. Not in this one. For this one it is. Not in this one. Q0 equals 0. But in this one, Q0 equals 1. And in this one, Q0 equals 0. So that means only this state matters. And what we have to do is find all the places where something's coming in now. We've got an arrow coming here. We've got an arrow coming here. Oh, let me just erase this all. It's recorded, so you guys can always just go back. So we got an arrow coming here. An arrow coming here. One coming here. Oh, hold on. And then one coming here. And you might think, well, how do you know when to stop? Like, why wouldn't something like this going all the way around be a thing going in? And the answer to that is when you go as far back as you can until you hit a state. So when you're here and you go back to this purple one, you eventually hit a state, so it stops there. When you go here, you keep going back up. And then, oh, so we didn't hit state yet, so it would have to keep going. And then, yeah, so that's how it is. So based off that, for the green one, that would be 0, 0. So both Q1 and Q0 are 0, so Q, hold on. Actually, yeah, we're doing it for Q0 prime. So the green one, Q0 prime, Q. We can do it in better order. Q1 prime, Q0 prime, and then x2 was 1, so it's just x2. Then x1 was 1, so it was 1. And then x3 was 0, x3 prime. So that's that green term. Let's see if that's what he did. Is that this one? Just copy and paste it up there. So we got Q1 prime, Q0 prime, x3 prime, x2, x1. Yeah. So that right there is the green path. Let's do the purple path. Purple path, well, it also comes from from 0, 0, so it's going to be Q prime, 0 prime, and then when x2 is 0. So x2 prime. So yeah, that's this one. So yeah, and then the red one, if you want, you can pause the video and see if you get it right, or you can just keep watching. Okay, well, if you paused it and you're returning, the first step would be to see that this is state 1. So this would be 0, 1. So Q1 is going to be primed because it's 0. Q0, it's just going to be Q0 because it's 1. And then X2 is prime because it's 0. And then let's see if that's down there somewhere. Yeah, I think this one was it. Yep. And then let's do the last one. So last one is state 1, 0. That's going to be Q1, Q0 prime, and then it's X1 prime. I mean, yeah, X1 prime. So it takes the 0 path. So yeah, that's how you do that. Just erase this now. It's all recorded, so it's not like anything's being lost. So yeah, what you guys are going to need to do, get Q1 prime, and this is for your lab, not the example one I made, but the example one has everything all worked out. So for Q1, this is 0, 0, this is 0, 1, 1, 0. So the only state that matters is this one. You're going to have to identify all of the paths coming in from each place. And yeah, I won't do it all, but I'm not gonna do any, but just kind of giving you a little preview. So yeah, you just gotta do the same thing we did. So there's path coming in through here, path coming in through there, and I think this path coming into through there. And here, let me just write it better. Okay, so you got 3 paths. I think there's only 3. Yeah, you can't go this way because it just goes in there. So yeah, you got your 3 paths, and then based off that, you'll just do what we did earlier, and then get your equation for this one. And then for Z2 and Z3, you do the same thing that we did earlier. So that's how you would get your equations for this one. And then once you have your equations, just all of this code that I wrote, I just went overkill and just did the entire thing from scratch. You guys, your only job is to either get the equations and then put them there, and then instantiate the D flip-flops correctly. And then this too. Actually, no, this is already instantiated, I think. Or you can So yeah, one way of doing it is with this, or you can initialize the ROM module. So like, so yeah, the other way of doing it is to then just go through and fill out that table. So like in your lab, where's it? You guys would need to fill out these. And once you fill these out, you just initialize that in the ROM, in the code he's going to give you, and then you're done. And I'm guessing a lot of people found this helpful, just doing it, showing it on your own thing. So I guess I'll go ahead and show how to do it with the ROM way too. So for this one, state 0, the inputs is 0. Just trace that out. So the state 0, what that means is we're right here. If the inputs is 0, then that means x2 is 0, x1 is 0, and x2 is 0. So that means we're going to go down this path, and we're going to go into state 1. State 1 is this. So for state 1, that means Q1, Q0 are going to be this respectively, and the only thing that turns on along the way is Z2. G2 is 1, 1 is 0, 0. So this is going to be the first row. So yeah, we go to state 1, and then Z2 is the only thing on. Honestly, if you've made it this far, like if you watch the entire video, we'll just do, say, this one, to give you guys an example. We're in state 0, 1. So we're in state 0, 1, which is right here. 0, 1, and the inputs are 1, 1, 0. So x3 and x2 are 1. x3 and x2 are 1. Mark it down. Actually, I can remember. So x3 and x2 are 1, x1 is 0. So based off that, well, we reach x2. What was x2? x2 was 1. So we're going to go there. Meaning, so we started off, because remember, this state is 0, 1. That's what we started off, so meaning Q1 was 0, Q0 was 1. So these are like the first things in the table. And then from all that, we can see that the next state, it goes from 0, 1 to state 2, just 1, 0. So that means, like, so this was like, and then the only output in that state is Z1. not evens. Is that row? Which one was that? Was it this one? Yeah, I think that was it. Because yeah, we're in 0, 1, state 0, 1, and then x3 and x2 are 1, which goes there, meaning the next state is state 2. So yeah, then these outputs would be and then the only thing that we saw that turned on was Z1. Yeah, Z1. Right? Let's do another one. Just to reward the people who have made it a full hour and 18 minutes. Because if you watched this entire thing, you've clearly learned a lot, I'm sure. You haven't even gone through the code yet yourself. You've just been watching. Yeah, I highly recommend to open up the file that I put in Blackboard. I wrote every single one of those completely from scratch. So it should be understandable, hopefully. If not, in the future, I might want to release a document explaining everything in detail, what's going on with each module. But for now, I think it's intuitive. But I don't know, I'll see what you guys think. But yeah, just to reward you people, whoever's made it this far, we'll do another one. Another one. So when we were in state 2, 1, 0, just erase this all. So when we were in state 2 and all the inputs, okay, when it's 1, 0, 0, it's x3, 1, x2, 0, 1, 0. So from that, it quickly goes there. That means next state is going to be 0, 1. And when we go from here to here, we did not run into any bubbles. But when we do get into this state, it is Z1. So that means Z3 is 0, 2 is 0, but Z1 is 1. Meaning we go down. Z1 is 1. And go to state 1. You see. Yeah. Seems right. Let's see. 3, 2, 3. Yep. Well, that's how you do those 2 rows. So yeah. And then you just have to repeat that entire process for these and these and these. And you guys will be expected to do both implementations with equations and with the ROM. It should be easy because I already gave you, I mean, if you did your homework and watched this entire video, you got 2 of the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. You got 2 out of 16. That's 1/8. That's 12.5%, I believe. Yep, 12.5%. So if you've made it this far to the video, you've already gotten 12.5% of the second part done. And then Morton just flat out gave you this. He didn't really give you much of an explanation as to where this came from, but if you rewind the video, you'll see how he got this. And I guess just to reward the people who've gotten this far, I'll show you guys a very powerful tool to simplify your equations. Yeah, I know there's a lot of people who probably just aren't going to even watch the entire thing, so they're going to miss out. So I'm always going to make it where these videos are worth watching every last bit. So this, like you see, we have this ugly equation right here. Oh, hold on. In this calculator, actually, you know what? You don't have B1, just make it X, Y, Z. So if you enter in a Boolean equation, press go, it simplifies it. Now, I don't think you can enter numbers. Like if you do Q1, it's going to interpret that 1 as a logical 1. So don't do that. Instead, just memorize that X would be equal to like Q0, and then Y would be your Q1, and then Z would be your X0, and so forth. So this is a very powerful tool to just get it instantly. Simplified. Now, Morton doesn't care if you simplify or not. It's just a matter of getting it to work. But if you want to simplify it instantly, this is a very powerful tool to simplify anything instantly. So yeah, this is your lab, and this example will be posted on Blackboard, and it's a complete example. So this is a state machine. These are the equations. There's some work showing how you get the equations. And this is what actually happens from a block diagram standpoint. This is the ROM version. And then the code for that is in these, and then this is the constraint file. And also made a test bench in case anyone wants to test the ROM. So let me just show you guys how that would work. And then there's the top level module test bench too. Okay, so it's already here. So when you want to test one module, oh wait a minute, it's not here. Okay, so yeah, when we want to test the ROM, see how all these modules here? It's a top level module. There's a default module. All of these. If you just want to test one, you make the test bench for it, put it there, and then you have to delete the other ones that don't matter. Now you can run a test bench for your ROM. So what this test bench is going to do, it's going to manually inject these signals to be equal to the decimal value of 24. So 24. What we should see in the output is this. And then when 400 units of time go by and we change it to this, we should see in the output this value, so it's the same thing. So let's run that. So when we enter in, uses our inputs. Hold on. So yeah. So for both input combinations, only thing that went high was Z0. And that's exactly what should have happened. Only output Z0 got high. We assigned Z0 to be equal to in the very last bit of the index. So the index determines the row. So we have, you know how there's 32 bits? You know how there's 32 entries? So the 32 entries is represented by, hold on, of course. Yeah, we're about to finish this up real soon. So we have 32 entries. In order to represent each entry, you need how many bits? You need 5. So yeah. That's why the index has to be all 5. This would be like our 1, 0. Yeah. So yeah, that's like what the index is. And then the number shows what is what. Like, is it that one? Or is it that one? Or is it that one? So yeah. Actually, so yeah, the index chooses which row. And then the number chooses which one of these. So we want Z0 to be index 0, so that means this is Z0, then yeah, you guys get the point. But yeah. So yeah, this is everything you guys need to know for Lab 7. This was a very in-depth video about what's actually going on. I spent a lot of time making the examples, and yeah, I hope it helps.